Have you ever wondered where the universe keeps its most concentrated, mind-bending energy hidden? For thousands of years, humanity has basically relied on chemical reactions for power. We burn wood, we burn coal, which is really just us rearranging the outer electrons of atoms. But what if I told you that by peering way past those electrons, straight into the microscopic vault of the atomic nucleus itself, we unlock a scale of power that is literally millions of times greater?
Welcome to This Explainer. Today, we're diving deep into the quantum machinery of our universe. We're going to explore exactly how we can extract staggering amounts of energy by breaking apart heavy atoms, and how we might one day power our entire civilization by building artificial stars. Here is our roadmap for today. We'll start with 1, the power of the nucleus. Then 2, splitting the atom through fission. 3, controlling the chain reaction. 4, nature's ancient nuclear reactor. 5, star power and thermonuclear fusion. And finally, 6, the future of controlled fusion. All right, let's jump straight into part 1, the power of the nucleus and unlocking that microscopic fault. To really grasp nuclear energy, we have to completely reset our understanding of scale. Look at the sheer, uncompromising mathematics here. When we burn a single kilogram of coal, we're tinkering with those outer electrons, right? And that gives us enough chemical energy to run a standard 100-watt light bulb for maybe 8 hours. But if we take 1 kilogram of uranium-235 and completely fission it, meaning we rearrange the nucleons, the actual protons and neutrons inside, that exact same kilogram can power that exact same light bulb for 30,000 years. Think about that. The energy powering the device you're watching this on right now could be sustained for millennia with just a handful of uranium. It's a million-fold increase in power, pound for pound. Moving on to part 2, splitting the atom. Specifically, we'll look at fission and the Bohr-Wheeler liquid drop model. So how exactly do we get that energy out? Well, think of a uranium-235 nucleus like a pulsating, positively charged drop of liquid. When it absorbs a slow-moving thermal neutron, it gets this huge spike of excitation energy. The nucleus basically gets the jitters. It starts to wobble, stretch, and oscillate violently. Because all the protons inside are positively charged, they fiercely repel each other through electric force. As the drop stretches out, a sort of neck forms in the middle. If that electric repulsion manages to overcome the strong nuclear force that's desperately trying to hold it together, the neck just violently snaps. The nucleus breaks into 2 pieces, they fly apart at incredible speeds, and boom, fission has occurred. The absolutely crucial point here is what happens to the energy when that snap happens. We call this the disintegration energy, or just the Q value. See, because the 2 new fragments are more tightly bound than the original heavy nucleus, a tiny, almost imperceptible amount of mass is lost in the process. According to Einstein's famous equation, E equals mc squared, that missing mass doesn't just vanish, it's converted entirely into energy. For a single uranium-235 atom, this releases approximately 200 mega-electron volts, or MeV. And remember, that is just for one single atom. Which brings us to part 3, controlling the chain reaction, or harnessing the break. We've seen how one atom splits, but to scale this up to billions of atoms and actually get usable power, we have to trigger a chain reaction. In a nuclear weapon, like a plutonium-239 test, it's uncontrolled. When an atom splits, it ejects extra neutrons. Those neutrons hit other atoms, they split too, releasing even more neutrons, and so on. This reaction spreads exponentially through the material in a fraction of a microsecond, releasing a devastating, unbelievable amount of energy all at once. But obviously, for a nuclear power plant, we need absolute, meticulous control. To harness this break safely, we basically have to do some intense subatomic bookkeeping. First off, the neutrons that fly out of a split atom are moving way too fast to easily split another uranium-235 atom. So we use what's called a moderator, typically just water in a pressurized water system. The fast neutrons crash into the water's hydrogen protons, losing kinetic energy until they calm down and become slow thermal neutrons. We also use control rods, which actively absorb neutrons to maintain a strict multiplication factor, known as K, of exactly 1. This means every single fission event triggers exactly 1 more fission event. Not 2, not 0, exactly 1. This is what keeps a reactor perfectly critical and stable. Human control over this incredible process truly began back in 1942. Enrico Fermi built a nuclear reactor in an old squash court at the University of Chicago. It wasn't some shiny sci-fi lab, it was a gritty, real-world pile of graphite blocks, which acted as the moderator, embedded with lumps of uranium. It was right there that humanity achieved the very first artificial, self-sustaining nuclear chain reaction. Now let's shift gears for part 4, nature's ancient nuclear reactor, also known as the Gabon anomaly. So it's supernatural to think Fermi's squash court pile was the first time a chain reaction ever occurred on Earth. But did humans actually build the very first nuclear reactor? To answer this, we have to completely flip the script and look back, way, way back.
Today, natural uranium sitting in the ground only has about 0.7% of that fissionable uranium-235 isotope. The rest is mostly uranium-238. You literally can't run a standard light water reactor on that. You have to artificially enrich it to about 3 or 4%. But 2 billion years ago, because uranium-235 decays faster than 238, its natural abundance in the ground was already at 3.8%. In a place called Gabon in West Africa, groundwater seeped into these incredibly rich uranium deposits. That water acted as a natural moderator, slowing the neutrons down, and an actual, spontaneous, underground nuclear reactor just fired up all on its own. And we know this for an absolute fact because today we can find specific fission byproducts, like rare isotopes of neodymium, left over in those exact rocks. Nature literally beat us to the punch by 2 eons.
All right, moving into part 5, star power, thermonuclear fusion, and how we build heavier elements.
Okay, so far we've been entirely focused on breaking heavy atoms apart. Now let's pivot. The crucial takeaway here is understanding this massive contrast. Fission is splitting massive, loosely bound nuclei like uranium, which happens relatively easily if you just tap them with a neutron. But fusion? Fusion is the exact opposite. It's taking incredibly light, tightly bound nuclei like hydrogen and smashing them together to form something heavier, like helium. This actually yields even more energy per unit of mass than fission, but as we'll see, it is ridiculously difficult to trigger. The main villain in our fusion story is something called the Coulomb barrier. Because atomic nuclei are positively charged, they desperately, fiercely want to push away from each other. Think of it as the ultimate subatomic force field. To get 2 protons close enough for the strong nuclear force to finally grab them and snap them together, you have to overcome an electric repulsion barrier of about 400 kiloelectron volts. To tunnel through that barrier, particles need to be moving at astronomical speeds, which means you need astronomical temperatures, literally the kind of heat you only find in the center of a star.
And honestly, this brings us to how our own sun actually shines. It uses something called the proton-proton cycle. It's this incredible multi-step subatomic dance. First, 2 protons smash together in the extreme heat, fusing into a deuteron while spitting out a neutrino and a positron. That positron almost instantly collides with an electron, annihilating in a brilliant flash of gamma-ray energy. Through further incredibly energetic collisions, these particles eventually build a stable helium nucleus. So hydrogen is the fuel, helium is the ash, and that tiny bit of missing mass, that's what bathes our entire solar system in light and heat.
Finally, let's look at part 6, the future, controlled fusion, and the quest to build a star in a jar. If nature can do it in the stars, can we do it here? Well, to build a star in a jar on Earth, we can't really use that slow proton-proton cycle. Instead, we use heavier isotopes of hydrogen, deuterium and tritium. But to get them to fuse, we have to create conditions that are, frankly, mind-boggling. We need to strip the electrons away to form a glowing, neutral plasma, and then heat that plasma to temperatures exceeding 400 million Kelvin. That is vastly hotter than the core of the sun itself, all while keeping it incredibly dense. To pull this off, engineers are desperately trying to cross an absolute mathematical threshold called Lawson's criterion. It basically dictates the rules of the game. You have to hold enough particles together, that's your density n, for a long enough time, that's your confinement time t, to get a self-sustaining burn. The product of that density and time must be greater than 10 to the 20th power seconds per cubic meter. It's like a high-tech digital readout that plasma physicists stare at every single day, trying to achieve ignition. To actually confine these miniature terrestrial stars today, we basically have 2 incredibly sci-fi approaches. The first is magnetic confinement. Because the plasma is so hot, it would instantly melt any physical container, we trap it inside a donut-shaped magnetic force field called a tokamak. The second approach is inertial confinement. Here, we take a tiny, solid pellet of fusion fuel and zap it from all sides simultaneously with some of the most intense lasers on planet Earth. The outside of the pellet boils off instantly, creating a massive inward shockwave that crushes the core, sparking fusion for just a tiny fraction of a second. Both of these methods are sitting right at the absolute bleeding edge of human engineering. So, we've journeyed all the way from splitting uranium atoms like wobbling water drops to finding ancient reactors buried deep in the earth, straight through to replicating the fiery hearts of stars with lasers and magnets. It just goes to show exactly how far we've come in understanding the hidden, incredible power locked inside matter. But it leaves us with one lingering thought, especially as we look to a future that is so desperate for clean, limitless energy. As we continue to map the quantum mechanics of the cosmos, are we finally ready to wield the power of the stars? Thank you so much for joining me in this explainer. Keep wondering, keep learning, and I'll see you next time.